Now, let's look at a few more interesting and important concepts regarding the binomial trees. One, trying to cut an n period binomial tree which gives 2 power n possible outcomes to a slightly lesser number of possible outcomes, which can be accomplished using the recombining binomial tree. So let's try to discuss on what is that goes as a part of this recombining binomial trees. Then what are the different ways of calibrating the binomial models? And finally, we'll see how do I use the real world probability measure and use a concept of state price deflator approach for valuing the derivative security. So initially, let's get started with this recombining binomial tree. See, earlier when we talked about a two period binomial tree, we said S naught times U, S naught times D in the first period. Then it can go to S naught U1, U2, S naught U1, D2. Then S naught D1, U2, S naught D1, D2. This is a typical two period binomial tree approach. Now, like this, if we have the third period, then we have 8 different possibilities because 2 come out from each of them. Similarly, if I am having a fourth period, there could be 16. So overall for the nth period, there could be 2 power n possibilities. Now, this recombining binomial tree approach, what it does is, I will try to make, okay, S naught times U, S naught times D. And here, one part, okay, there is a U and a U, but a D, whether it is U and a D or a D and a U, we match it to the same stuff. So the up movement is stable throughout, the down movement is also stable throughout, which means when I am taking S naught U times D or S naught D times U, both mean the same for me. And in other way, probably it's as good as I'm making U1 equal to U2 equal to UN equal to U, D1 equal to D2 equal to Dn equal to D. So this is what we are doing as a part of the recombining binomial tree, which means even Q1 equal to Q2 equal to so on Qn equal to Q. Simplifies the process. So overall the probability of moving up is e power r minus d divided by u minus d. So this is what typically comes up as a part of the recombining binomial tree approach. So as simple as this, we are seeing this is a very simplified kind of a model, right? And because of this, what we see is in the nth period, we get only n plus 1 possible states. In the third period, in the second period, we get only 3 states. In the third period, we'll get only 4 states. So in the nth period, we are going to get only n states. But let's try to understand there the typical model like this, though it is complex, it's very flexible because I can change the use at each of the periods. I can change the D's at each of the periods. I can change the Q's. I can find different Q's at each of the periods. So different levels of volatility, the price changes, the up and down movement changes for each of the periods, for each of the states can very well be incorporated in this particular model. But the only drawback being the number of states that are going to come up right? Even for 3 periods, I'm going to get 8 different possibilities. So even if I'm going for a 3 period binomial tree, I may end up with 8 states. 5 period binomial tree, I may end up with 32 states. And computation time as well as the computation efforts that are typically required is going to be quite drastically large. And the benefit that may be derived out of the extra benefit that I may get in the value of the derivative may not be significantly different. That is where this concept of recombining binomial tree approach has been looked at, wherein I make an assumption that all the u's are the same, all the step ups, all the step downs are the same. If that's the case, the q also will remain the same, because at the end q is nothing but e power r minus d by u minus d. So when d and u, both of them are the same, the q also across all the periods is going to be the same, which means at any point, if I have to find out the price at a time period t, it's as good as s naught time up movements. Probably there could be some nt number of up movements, and the down movements there could be totally t minus nt of them. So this would be the price at a time period t for each of the approaches, depending on each of the times. So number of up movements, number of down movements, I'm trying to find out the price at a time period t. So number of steps that it has gone up and number of steps that it has gone down. So the number of stages at any point now, the number of the typical states at this point is going to be n plus 1 only, whereas in the non-recombined kind of a model, the number of states used to be 2 power n. That used to be pretty drastically higher. So in a simple word, even if I am going with 9 day binomial tree kind of a model, earlier I used to get 512 different states, whereas now we get only 10 states. The computation becomes more and more simplified, right? So we are going to reduce the computing time drastically, and let's understand this is more and more applicable only when the payoff on the derivative security is not path dependent. If the derivative securities payoff is path dependent, what do I mean by path dependent? Okay, here if I say this price, this payoff will be different if the previous is, or probably if you say S4, right? If S4 comes either from S1 with a down or from S2 with a up, if it really doesn't matter, that is called path independent. In what route it has reached the destination is typically is not mattering to us. Whereas if I say no, the payoff is going to be C4, if it comes from, if there is a fall, and it is C5 if there is an increase. If the previous state, if from the previous state there is a fall in the price, the payoff is going to be C4. If from the previous state there is a rise in the price, the payoff is going to be C5. That is what we call as path dependency. Means the way you are reaching that particular payoff level based on the previous states really matters in the deciding of the payoff. That is called as the path dependency. There are some kind of exotic options which typically play a path dependency. We see what is called as Asian options, which are more and more path dependent. So I cannot use this kind of recombining binomial tree approach for them. Whereas a regular European kind of options which are not path dependent I can very well use the recombining binomial tree approach. So here in the in a recombining kind of a scenario, the overall payoff is based on number of up movements, number of down movements during that period. The order of the movements really does not matter. Whereas when we are talking about a path dependent process, along with the number of up as well as number of down movements, even the order of the movements also will play a role in deciding the payoff. Right? So that is the reason for those kind of options which are not path dependent, the recombining binomial tree approach simplifies the calculation, improves the output quite drastically, but this concept will not work for those kind of options which are path dependent, right? So the n period binomial tree model, when we are, so n period binomial tree model, when we are doing a recombining of the trees, we are going to get n plus 1 states, and this kind of a recombined binomial tree, in other words, is also called as a binomial lattice. That recombined binomial tree, whatever is created, that is called as n period binomial lattice. The binomial lattice is something which is a binomial tree which is recombined using u1, u2, u3 same as u, d1, d2, d3 same as d. So here when we see this kind of a process, it's as good as s naught, s naught u, s naught d. This becomes s naught u squared, s naught ud, s naught d squared, s naught u cube, s naught u squared d, s naught ud squared, s naught d cube. Now if you see the way these are coming out, the s naught u squared d comes out in three different parts: UUD, UDU, DUU. Three parts. Similarly, this comes in three parts. This is one, this is one. Now, if you are typically seeing the probabilities that are coming out here, the Q's, e power r minus d by u minus d, for every stage the Q's are going to be the same. And all these steps are typically independent. So overall, if I want to know the number of steps up to the time period t, right, the number of steps that has led to this, if I want to find out, I am simply looking at it as a binomial distribution with the number of periods, let's say n, and the probability of movement q. So the total number of steps up to a time period t, it is completely a random variable following a binomial distribution, and it is completely independent of n minus nt, number of up steps is completely non-overlapping time intervals, it is completely independent. Now I can simply find out the price of this particular derivative simply as find out the present value. It's as good as I try to find the payoffs at each of these periods, right? Whatever is the payoff at each of the periods, number of up movements, expected value is nothing but based on the binomial tree. I'll find out the expected value and discount it to the present value. So in case of a n period binomial tree, we are simply finding out the price of the derivative security by going ahead with whatever the function of st times the up movement, let's say k number of up movements, and n minus t minus k number of down moments. So this is the kind of payoff. This I am typically adding it over 0 to n minus t periods, and this I am discounting it e power minus r times n minus t, and the number of combinations of each of them n minus t factorial, we get it as n minus t ck. So I am writing it as n minus t factorial by n minus t minus k factorial times k factorial, n minus t ck into q power k into 1 minus q to the power of n minus t minus k. So this is the total present value of the derivative. We can directly put it into the numbers and can directly find out. The concept of finding out the value of the security remains the same. The only difference being, instead of having multiple states in time period n, we have reduced it to a lesser number of states by doing the recombining the binomial trees, right? So now we will move on to our next concept. How do we typically calibrate binomial model? Here we say that for this binomial model, the mean as well as variance, whatever going as a part of the binomial model, we'll try to see that they correspond to the mean and the variance of a log normal distribution model. The reason being, the prices typically are assumed to follow a log normal kind of a distribution, right? And in a continuous time, this binomial tree is more in a point of discrete time model, whereas the log normal is more of a continuous. So in a continuous scenario, there is this particular model can very well approximate to a log normal kind of a model. So we will take the mean and the variance of this particular model, the computation of the mean and the variance while calibrating the binomial model will take them on the similar lines as the mean and the variance of an equivalent log normal model. And we also, especially if we are considering the recombining binomial trees, here one more additional thing that we try to create as a relationship between u and d is u equal to 1 by d. So these two things. The first thing is we make sure that the mean and the variance for our binomial model will be similar to the mean and the variance that gets created from the equivalent log normal model. And in case we are doing the modeling for a recombining binomial tree, we'll try to ensure that the up factor is same as the reciprocal of the down factor. Now going with these two things. The first part talking about any log normal model, we say that if I can exhibit the stock prices like this, the DST alpha times ST times DT plus sigma ST dBT. This is what is the differential equation. This is what is a differential equation for the geometric Brownian motion. So here we have said earlier that St by S0 will follow a log normal distribution with the parameters alpha minus half sigma squared times t and the variance being sigma squared t. Now which means the logarithm of St by S0 is going to follow a normal distribution with alpha minus half sigma squared times t and sigma squared times t being the variance. And of course, if I am taking t0, I mean s of t divided by s of t0, I could very well convert it into the normal. Here the alpha for me is r, the risk-free rate of return. minus half sigma squared times t minus t0 and sigma squared times t minus t0 being the variance. So which means from this I can very well find out the expected value of S st, which is nothing but t plus delta t, given st is nothing but I can take this part, which is the expected value, which is the e to the power of r delta t, and similarly I can take the variance of this entire log of st plus delta t given st. This I can take it as sigma squared t. And now we already know that this is same as q times the up moment plus 1 minus q times the down. So from here I can very well simplify. This is the expected value. So which is directly coming out for me, q times up moment 1 minus q times the d is same as e power r delta t. So from here I can very well simplify my q e power r delta t minus d divided by u minus d. The same logic if I'm going with variance. So if I want to find out the variance of the log s of t plus delta t given s of t. Now the same logic I substitute all this stuff. Now I can very well say this is q times. Now I'll substitute it. So q times I get log u squared plus 1 minus q times minus log u squared minus expected value of log of s t plus delta t given st squared. Now overall this is working out to log u squared minus expected value of log s of t plus delta t given st squared. Now this part, right, this entire thing is f of some function of delta t squared. And as delta t is going up higher and higher and higher, as delta t is approaching zero, minute and minute, we see this f of is going closer to 0. So overall I can very well say the variance is nothing but the log u squared. The variance is nothing but log u squared, and this we can very well write it as sigma squared times delta t. So this entire thing is coming out to sigma squared times delta t. So from here you are directly getting u is nothing but, so log u squared, the variance, I will equate it to sigma squared times delta t. So log u will become sigma times square root of delta t, and u will become the e to the power of sigma root delta t. So because u is 1 by d, d will become e power minus sigma times square root of delta t. So when we are using a typical calibration model here, the up moment directly will take it as e power sigma root delta t. The down moment d will take it as e power minus sigma times square root of delta t. So this is how the typical computation comes out. And in case there is any kind of dividend, this is for a non-dividend paying kind of a security. In case there is a continuously payable kind of a dividend on this asset, I'll simply make it as e power sigma root delta t plus v delta t, whatever is the dividend that is typically being paid. And d also becomes e power minus sigma root delta t plus v delta t. So whatever is the continuous dividend that is typically payable, that would simply be substituted to compute the u and d, and from there we are computing the probability of moving up, which is the q, e power r delta t minus d divided by u minus d. This is the typical mechanism that we are using when we are going with a recombining binomial tree kind of an approach, right? And one more important thing that we are discussing here is the state price deflator approach. It's basically, see, we have been talking about a typical risk neutral kind of a pricing. V naught, we said e power minus r, the q expected value of v1, right? So which we also said it is e power minus r times what is the expected value? The risk neutral probability of going up multiplied by the value at time it is going up, the value of the derivative when it goes up, plus 1 minus q times the value of the derivative when it is going down. Now what I am simply doing here is I'll just do e power minus r. Q, I will write it as, right, instead of q I'll write it as p times q by p times cu. This also I'll write it as 1 minus p times 1 minus q by 1 minus p times cd. So this is nothing but if I see this e power minus r times, right, if I say p times some number q by p times cu plus 1 minus p times 1 minus q by 1 minus p times cd. It's again as good as saying e power minus r times some p, some 1 minus p. This is the up movement now. This is the down movement now. So if I am taking out, right, if I am taking out in this case, I could very well write it as the expected value A1 V1, wherein I am depending on A1 here as e power minus r times q by p when the price has gone up, e power minus r times 1 minus q by 1 minus p when the price has typically gone down. So that times the V1, which is giving me the value. So that is where we are calling the A1, which takes a value e power minus r times q by p when S1 is S naught u, which will be equal to e power minus r times 1 minus q by 1 minus p when S1 becomes S naught times d. This A1 is typically called as the state price deflator. In some cases it is just called deflator. It is called as state price density. It's also called as stochastic discount factor. So the probability it's simply coming out as the probability that the stock price is going up multiplied by the value of the derivative if the stock price goes up, plus the probability that the stock price will go down multiplied by the derivative's value when the price is going down. So it is simply working out for us that whatever is the V0, it is coming out as the real world probability measure of A1 times S1. Typically, when we are looking at the V1 being equal to S1, then we can take V naught is EP, which is the expected value using a real world probability measure. Use the state price deflator times the price of the share. The same logic goes even in case of n period binomial tree or a binomial lattice as well. Typically, even in that case, the AN, which is the n period state price deflator, will get extended as e power minus Rn q by b to the power of n, the number of up movements into 1 minus q by 1 minus p to the power of n minus nn. So the number of up movements, number of down movements. Again, this becomes my state price deflator. So this is another mechanism which we can use typically to price the security. Either I can go with a risk neutral kind of a pricing measure, or I can very well go ahead with a real world probability measure using the state price deflator kind of an approach. So these two things are typically giving us the same kind of a solution, though the process that is being used to arrive at the pricing is different. Right, so even in that case, the fair price of the derivative security comes out as the p-type expected value of an, the n period measure, the value at the nth period. So this is some way where we can typically, this really helps us in terms of valuing the price of the derivative security, whether using the risk neutral or even a real world kind of probability measures. All right.